Hello, my dear students. Welcome back to the session. Last session we discussed RL series circuit. Okay, now let's look at RC series circuit. Okay, I think you might have understood how I have just gone the same flow you maintain even for RC series circuit. Okay, it will be a good practice for you. Kepler minus, yeah, this is C, right? Minus JXC. V and I. VR. This is VC. Okay. The same way you can proceed. R minus JXC. What is the assumption here? I is equal to I at an angle of V. Then V becomes what? V at an angle of phi. Finally, the phase difference must be phi. Okay. R square, X square minus tan inverse XC by R. Multiplying both sides with I, then what do you get? It becomes V magnitude I into R minus J magnitude I into XC. Finally, you got VR magnitude minus J VC, which is nothing but root VR square plus VC square. Okay, at an angle of minus tan inverse VC by VR. S is equal to V into I conjugate. Again, you know that. Now here, angle phi, should we take angle phi? That angle phi is positive, but current should lead. If current is to be lead, okay, then definitely it must be what? Minus phi, not phi. Phi is positive, but minus. If it is 30, then minus 30 degrees. Okay, so therefore, V at an angle of minus phi, then I at an angle of 0. Conjugate is also 0. Finally, you get what? Minus phi. So finally, you got here, okay, Vi cos phi minus j Vi sin phi. Okay, Vi cos phi minus j Vi sin phi. This is actually P minus j. Okay, this is P minus j QC, where P is equal to Vi cos phi. Nothing but again you can write the same formulas. I told you already, I square R or VR square by R. So no, remember always the formulas like, you know, IR square R. Don't remember as I square R. You will definitely make a mistake. Remember the formulas always as Vi cos phi, IR square R. Here IR and I both are same, no doubt. Because series circuit, I, IR, IC all are same, no doubt. But when you remember the formula active power, remember as Vi cos phi, IR square R, VR square by R. These two are related to the resistor and this is related to the source. The source power is nothing but the resistive power. Source active power is nothing but the power comes in with the resistor. Understand all of you? Okay. Next, QC Vi sin phi. IC square XC. But I and IC both are same here in this context. But always remember IC square XC, IL square XL, VL square by XL, VC square by XC. This is how you need to remember the formula. Don't take it as I square R, V square by R. I'm telling you that is going to be a big mistake. Okay? You're going to commit a lot of mistakes in the calculation. Better you always remember like this. VC square by XC. That's it. Getting all of you? Then when you come to the phasor diagram, I am taking current as a reference phasor. Then VR is nothing but what? I into R. Okay, this is VR. Then current should lead or voltage should lag. So V is equal to I into XC. The resulting phasor is nothing but V, nothing but root VR square plus VC square. This is nothing but I into Z. Okay, this is phi. These are all magnitudes, Nana. Okay, I may not write sometimes, but you must be understanding that these are all magnitudes. You're dealing with magnitudes. Don't forget that you're dealing with magnitudes. All are magnitudes. That's it. Okay. Now here, if I take multiplying each phasor by I, then this is R, this is XC, this is phi. Z is equal to R square plus XC square. Okay. Then power. Power should be upward triangle or downward triangle? Definitely downward triangle, because the power is P minus JQC form because it is capacitive. So it is in fourth quadrant. Then multiplying each phasor by I, then I square R, actually IR square R, but in this context both are same. So I square R, nothing but active power P. QC is equal to I square XC. Then S is nothing but P square plus QC square, angle phi. Okay. You can write here I square, because this is also S magnitude, right? You are actually dealing with what S magnitude only. So you can write I square into Z magnitude. Getting all of you, see, apparent power is always written as, when you write phasor, a complex value V into I conjugate. Getting all of you? So you can write magnitude S is equal to magnitude V into magnitude I. It is not a problem. I can write like this. And you can also write S is equal to V square into what? I is nothing but V by Z. I is nothing but V by Z. Z magnitudes I'm dealing with again. Okay. So what do you get here? V square by Z magnitude. Or else S is equal to, when you write V is equal to IZ, I into, okay, Z, I into Z, I square Z. Getting all of you? Okay. But you cannot write S is equal to simply I square Z. No. Understand? Because conjugate is there. You cannot write like this. S is not equal to V square by Z. Understand? But S is equal, S magnitude is equal to V square by Z magnitude. Magnitude V square by magnitude Z. Magnitude I square into magnitude Z. But you cannot write simply complex values like this. Understand all of you? Okay. So remember, here since I am just denoting all these things magnitudes, so I am writing I square into Z, but magnitudes I am dealing with. I square into X, I square into R. So please note down this, all of you. Okay. I think all of you understand this. Now let me work out on RLC series circuit. Fifth one, sixth one, okay, sixth one, sixth one. I hope the previous one is fifth one, right? R, L, C, RL, RC, 5 over sixth one, okay? R plus JXL minus JXC. V and I. This is VR, this is VL, this is VC. VL, VR, okay, like this. Now let me take Z is equal to R plus J XL minus XC. Okay. I can take case 1. If XL is greater than XC, okay, if XL is greater than XC, what will happen? XL is greater than XC, it is a positive value. R plus JX, so it is inductive. Yes or no? So it is acting like what? Inductive circuit or lagging power factor circuit. Now Z becomes R plus J, it remains XL minus XC, okay, which is nothing but R square plus XL minus XC whole square tan inverse XL minus XC by R. Okay. If you multiply both sides with capital I into Z, nothing but V is equal to I into R plus J, I into XL minus XC. This I is a magnitude. Okay. I am just taking, let me write clearly. I into Z, multiplying both sides with capital I. Assuming that I is equal to I at an angle of 0, then obviously here it is inductive circuit. Okay, since it is inductive circuit, let me assume I is equal to I at an angle of 0. Then V becomes V at an angle of phi. Voltage should lead the current, or current should lag the voltage. Okay, so what will happen if you take that particular case here for your convenience? So VR plus J VL minus VC. VL minus VC. Yes or no? This is what you got. Is equal to root now VR square plus, how do you write? VL minus VC whole square at an angle of tan inverse VL minus VC by VR. Clear, all of you? Okay. So this is how you deal with. Okay. Now S is equal to V into I conjugate V into I at an angle of phi, because I is I at an angle of 0, V is equal to V at an angle of phi. Phi is a positive value because voltage should lead current, because already it is taken as 0. So from this we understand S is equal to Vi cos phi plus J Vi sin phi. Get it? So this is the active power, and this is the reactive power of resultant reactive power. It is resultant reactive power, QL minus QC. Very important. So what is P actually here? P can be written as Vi cos phi, or else IR square R. Here I and IR both are same. VR square by R. Always remember the formulas like this. QL minus QC is known actually here. Resulting reactive power is known, but I want individual reactive powers. So what is QL? QL is, okay, IL square XL or VL square by XL. I hope you understand the importance of these formulas. QC is equal to I square, IC square XC, but IC, IL, IR all are same. VC square by XC. Getting all of this is the lagging reactive power. This is the leading reactive power. Okay, some people write without lead, they put minus sign. Some people do not put minus sign, but they simply mention lead. But ultimately, what is the resulting reactive power? It should reduce. Yes or no? Either it is QL minus QC or QC minus QL. Generally, in this case, you are taking what QL minus QC. You are supposed to get lower, I mean less than the lowest value, because you are going to subtract. Yes or no, all of you? You are going to subtract. I mean, you are going to subtract these two. Therefore, the net reactive power will decrease. Not, I take my statement back that the net reactive power is less than minimum value. That's not the correct statement, but definitely I can say that the net reactive power will decrease. Understand, all of you? Well, so this is very, very important here. Right. Now the phasor diagram. Let's look at the phasor diagram. Okay. I hope you understand the meaning of it, right? Suppose in an example, I'll give you an example. I'll give an example. For example, you have active power is equal to some 20 watt. QL is equal to, okay, some 30 volt amp reactive. QC is equal to minus 10 volt amp reactive. So what is actually the net reactive power? What is the net reactive power? Tell me all of you. Net reactive power. Net reactive power. Okay, net reactive power, what will happen here? The net reactive power will become, now you are supposed to add these two. That means 30 minus 10. Sir, no? Because already negative sign is there. 30 plus of minus 10. So what do you get here? 20 volt amp reactive. Suppose the same thing, people write like this. Okay, people write like this. So what I'm trying to do is here plus of minus 10. That means I'm taking the addition of it. Understand? Because already negative sign is there. I'm just adding these two. But now if I say P is equal to some 20 watt, some QL is equal to some 30 volt amp reactive lagging, then QC is some 10 volt amp reactive leading. They have clearly mentioned 30 volt amp reactive is a lagging, okay, 10 volt amp reactive is a leading. Then what is the net reactive power when you take here? You are supposed to subtract this from this. So finally you get again 20 volt amp reactive only. I hope you understand the point. Okay. Finally, you must get the resultant is always, that is subtraction between the active and reactive power only, no doubt. You will get negative sign because it's going to reduce. Here I'm adding because all the negative sign is there. Here I'm subtracting because here positive sign is there, but I understand this leading, this is lagging. Then I should subtract, I understand that. Now here I cannot subtract 30 minus of minus 10, I cannot put it. Understand? Already here it's mentioned minus, so I simply add, whereas here I subtract. Look at this, the difference is that. Understand all of you? So net reactive power should definitely decrease. No doubt that will be less than the highest value, no doubt, because 30 minus 10, then this resultant is less than what? This 30 only. Yes or no, all of you? Okay. So it's very, very important. And let me now draw the phasor diagram. First you take down this, then I'll just draw the phasor diagram. Okay. Write down clearly, all of you. You have something like this. These are the powers given. Okay, what is the net reactive power? So let me mention even what is QLQC here. Okay, better, then only you will understand the meaning of it. 30 volt amp reactive, we know. Volt amp reactive is nothing but what? Reactive power. 10 volt amp reactive, but put it negative sign. This is plus, this is minus, clearly mentioning that it is lagging, it is leading. Okay. Instead of putting plus minus, he is writing now lagging and leading. So now here you are taking the addition of these two because already negative sign is there. So the net will become subtract, right? The net will decrease. Here you know that lagging and leading, but here negative sign is not given. Instead that, he gave leading. Therefore I am subtracting. Finally I have to get a resulting value that is less than the highest value. No doubt the net reactive power will decrease. Okay. So it's a very, very important point to be observed because in most of the times in our in a hurry calculations or in a faster calculations in the exam, we may do mistakes. So you must be very careful. Finally, the net reactive power should reduce. It is less than the highest value. Okay. Phasor diagram, when I draw, let me list out all the phasors required to be represented. I, VR, VL, VC, but V is equal to VR, VL, VC. I mean, I'm just writing here the phasor addition, okay? Complex, when I take V is equal to VR plus J, VL minus VC, that's the different story. but all phasors are supposed to be written, okay, are drawn on the phasor diagram. You are supposed to make the arrangement like this. First list out all the phasors to be represented, and also write the relation, some relation you want to maintain, right? So that is V is equal to VR, VL, VC. Okay. Then I'm taking here I. Then VR is in phase with IR and I same. VL leads IL, VL leads IL, and I am drawing at the tip of VR because I'm adding these. Okay. VL leads IL and I same. VC lags, that means here, since XL is greater than XC, then I into XL, that is VL is also greater than VC. So since XL is greater than XC, you also know that VL is greater than VC. Therefore, here, if I add this VC at the tip of this phasor, this is I into XL. Remember, I am dealing with magnitudes only. Don't forget that. I into XC. Okay. Let me add this phasor at this tip. So what will happen? This is VC. This total is VL. This is VC. Then what is the resultant here? VL minus VC. Okay. VL minus VC. Now this resultant phasor is, okay, here, because this is total VL, this is VC. What is the resultant? VL minus VC. Yes or no, all of you? Okay. So you would like to get that V is equal to VR plus VL plus VC, but VC is actually, this should be subtracted from this because it is actually having opposite direction to it. The resultant phasor V is equal to VR square plus VL minus VC whole square. Okay, this is angle phi, I into Z. Okay, so dividing each phasor R, dividing each phasor by I, then R XL minus XC, then Z, you will get R square plus XL minus XC whole square. Angle theta, nothing but phi. Both are same. Okay. Now multiply each phasor. Multiply each phasor by I. Just now we have seen. Then you will get. Still it is in first quadrant. That's why you get an upper triangle. Because P plus JQ, it is inductive, right? P plus JQ. So P QL minus QC. I square into XL minus XC. I square into R. S is equal to P square plus QL minus QC whole square. Okay. So note down this. Then we will move on to the second case. XC greater than XL. All this will help you a lot in locus diagrams, resonance. Okay, everywhere it is useful. This experience will help you a lot. That is why you do it systematically, and they must be fed in your mind. I'm telling you, on fingertips, you must be able to analyze easily the RLC series and parallel circuits. RC, RLC series and parallel circuits. Easily you can analyze if you permanently feed. Okay, come on, Nuda. XC greater than XL. Come on, Nuda. XC greater than XL. Case 2. XC greater than XL. Capacitive circuit. Behaves like capacitive circuit or leading power factor. Capacitive circuit or leading power factor circuit. Okay. Now definitely when I is equal to I at an angle of 0, V is equal to V at an angle of, you get minus phi. Yes or no? Now what will happen here? Z becomes R plus J X, R minus, because I'm taking negative common, minus common, Xc minus XL. Finally, I'm keeping this value positive because Xc greater than XL. Okay. So root R square plus Xc minus XL whole square. Okay. At an angle of minus tan inverse Xc minus XL by R. Then multiplying on both sides, I think need not explain you. Finally, I'm writing it. VR minus J VL minus VC. So I must justify here. Do I get negative sign all the time here? No, it may not be, because I've taken I is equal to I at an angle of 0. That is why I got negative angle. That is why I got A minus JB form. Understand? Okay. But to satisfying the condition here, current leads voltage, I can take n number of combinations here. This is 60 degrees, this is 30 degrees. Since both are positive values. This is 0 angle, this is minus 30 degrees. That means this is positive, this is negative. You understand? So need not be negative. Voltage current I cannot say, but I can say Z, I can say Y, I can say P. So what the forms that you are going to get, A plus JB form or A minus JB form? For impedance, admittance, power I can decide. But for voltage current I cannot. It all depends. Now which phasor you have taken 0, or which phasor angle which phasor you have taken as a reference phasor, and what is the angle of that reference phasor. It all say whether you get voltage A plus JB or A minus JB. Okay, so in this context, 0 angle, therefore you got negative, but does not mean that you always get negative here. Okay, but you get this magnitude always VR square plus V. This is VC, right? This is VC. What about this? VL. VC minus VL whole square. That's it. At an angle of what do you get? Minus tan inverse. Let me take this off. Minus tan inverse VC minus VL by VR. Get it? VC minus VL by VR. Okay. S is equal to, same again, you get V into I conjugate. Now you get VI at an angle of what? Minus phi is equal to VI cos phi minus JVI sin phi. This is P. This is QC minus QL, because X is greater than XL. Yes or no? Okay. Then what is P? You know very well. VI cos phi. VI cos phi. So what do you get here? IR square R. Nothing but VR square by R. QL. Okay. IL square XL. This is lagging. QC. IC square XC. This is leading. Right? So like that you can write. But QL minus QC can be written as VI sin phi. This is the net reactive power supplied by the source. This is the net reactive power absorbed by the inductor. Net reactive power absorbed by the capacitor. So QC minus QL you are going to take now. That resultant you are going to get the net reactive power. Okay, that's the reactive power, net reactive power. So what you get the phasor diagram here again? You get this is what I. This is what VR. Nothing but I into R. VC. I into XC. Next, VL, I into XL. Okay. From this, we get this VL must be added at the tip of VC. Then what do you get here? This is VL. So this result is what? VC minus VL. Yes or no? Nothing but I into XC minus XL. Yes or no? So you get now, this is what VR square plus VC minus VL whole square. Yes or no? All of you, I think, understand? This is angle phi. Now, dividing each phasor by capital I, R, XC minus XL, Z, downward triangle, because in fourth quadrant, you have a negative value here. Okay? R square plus XC minus XL whole. Okay? You people can do it easily. This is phi as well as theta, both are same. Angle phi and theta. Multiplying each phasor, then I square R, then I square XC minus XL, nothing but QC minus QL. Okay. Next, you want S is equal to root P square plus QC minus QL whole square. Angle phi. No doubt. So this is how you need to, for all these RLC series parallel circuits, you must be able to draw the phasor diagrams and the relations. All of them must be on your fingertips. Okay. All of them must be on your fingertips. You can't really search in the exam about the formulas. Okay. In the exam. So please note down quickly. I hope you have written this part. Okay. Case 3. Case 3. XL is equal to XC. It behaves like a resistive circuit or unity power factor circuit. Okay. When I is equal to I at an angle of 0, then V will also become what? V at an angle of 0. Yes or no? Z becomes R, V becomes VR, S becomes P. Right? No imaginary part at all. Then you have a phasor diagram I, then VR, VL equal, right? VC, I into XC, I into XL. If both are same, then the resulting phasor diagram will be something like this. I, okay, then V is equal to VR. That's it. This is for a pure resistor case, okay? So I think you have written this part, right? So let me take this one. Similarly, for RL parallel circuit, seventh one, RL parallel circuit. Minus JBL, G excited by a current source, okay, excited by a current source. This is the voltage source. Usually voltage source outside the circle arrow mark is placed to represent, okay, this is higher potential, this is lower potential. But here inside the circle only the current source is, the sinusoidal symbol and arrow mark is placed. This is capital I. You know that this is voltage V, no doubt. The same voltage will be maintained. but current divides, right? Because this is IR and this is IL. Okay. Then here 1 by Z is nothing but 1 by R plus 1 by JXL. Nothing but Y is equal to G minus JBL. You have G square plus BL square square root at an angle of minus tan inverse BL by G. Multiplying on both sides with capital V. So V into Y is equal to V into G minus J V into BL. Assume that V is equal to V at an angle of 0 because it is a parallel circuit. I told you already. You get I is equal to I at an angle of, because now here inductive current should lag. When current should lag means when already voltage is 0, definitely it must be minus 5. 5 is positive, but minus 5 totally it is negative angle. Okay. So what do you get here? I can write here that I is equal to, because V into Y is nothing but I. This is nothing but IR, current flowing through. Okay. The I and IR both are same. Okay. Because you know that it is V into G. Yes or no? What is the angle of V? 0. Angle of V is 0. Therefore, IR minus J, IL I can take. Therefore, square root IR square plus IL square at an angle of minus tan inverse IL by IR. Okay. S is equal to V into I conjugate. Okay. You know that V at an angle of 0. I is I at an angle of 5. Therefore, I conjugate will become minus 5. Conjugate will become 5. So finally, you got VI cos phi plus J VI sin phi. Okay. This is active power. This is the reactive power QL. So P will become VI cos phi. So I told you to remember always the formula as IR square R VR square by R. You can clearly understand you cannot write I square into R because I is different, IR is different. That is why I told you to remember always VI cos phi IR square into R or else 1 by G, okay, or into R, or else VR square, okay, by R or else into G. That's it. But what is VR in this context? VR and V both are same. In series circuit, IR, IL, I same. In parallel circuit, VR, VL, V all are same. Okay. So therefore, now that, but remember always the formula as IR square, VR square. Always remember. IR square R or IR square by G. VR square by R or VR square into G. Both are same. Then what is QL? VI sin phi. So what do you get? IL square into XL or 1 by BL. VL square by XL or into BL. That's it. I hope you understand. So note down that, okay, or just wait a minute because let me draw even phasor diagram also. What is the phasor diagram? Let us draw it. Let us also draw the phasor diagram here. So which phasor you are taking as a reference phasor? You have I, VR, VL. No, here you got I, V, and IR and IL. Yes or no? But you know that I is equal to IR plus IL. You want to maintain this relation, right? So then you just draw V and you draw IR. IR and VR both are in phase. But VR and V both are same here in this context. Therefore, IR nothing but V into G. Now, current lags behind the voltage IL, nothing but, okay, nothing but current lags the voltage V into BL. I is equal to IR square plus IL square. Angle phi. This is the magnitude, right? Yes or no? Magnitude. All are magnitudes. Sometimes I may not write clearly, but you must take them as magnitudes only. You're dealing with magnitudes, don't forget that. So V into Y. Yes or no? So divide each phasor by V. Okay. Then you get admittance. What is admittance? G minus JB. It is downward. Yes or no? This is G. This is BL. Divide each phasor. Then you get Y. Y is equal to G square plus BL square. Angle theta, nothing but phi. Both are same. Theta and phi. Multiply each phasor by V. V square into G. V square into G is nothing but P. But is it inductive or capacitive? Inductive. So power will be in the form of P plus JQ or P minus JQ? P plus JQ. So first quadrant or fourth quadrant? First quadrant. Then upper triangle or downward triangle? Upper triangle. That's it. P QL. V square into BL. V square into G. Yes or no? Is angle phi. S is equal to root P square QL square. This is magnitude. You can also write this one as V square into Y. Yes, you can write. When you deal with magnitude, this relation is correct. But when you deal with complex, S is a complex, V is a complex, Y is a complex, then this relation is not correct. Yes or no, all of you? I write here S is equal to V into I conjugate once again. Okay. S is equal to V square into Y is not correct. S is equal to I square by Y is not correct. Understand? But here S is equal to V into I is correct. Magnitudes. Okay. But V is equal to, okay, I by Y, or I is equal to V into Y. Then V square into Y is correct. Or else I square by, actually I square, okay, Z, but by Y you can take, okay, this is correct. When you deal with magnitude, these relations are okay. But when you deal with complex values, okay, this relation is not okay. You are supposed to maintain always V into I conjugate relation only. Now done this, all of you. So let me remove this meanwhile, okay, this part. Note down quickly. This is plus JBC because I'm taking now RC plus minus. Okay, note down that quickly. Meanwhile, I just take this off. Okay. Finish that, all of you. One by minus J XC. You get Y is equal to G plus J BC root G square plus BC square at an angle of tan inverse BC by G Again, you get I is equal to IR plus JIC. My assumption is V is equal to V at an angle of 0. I is equal to I at an angle of plus phi because this is capacitive. Okay. And I get plus here. It's not always correct because it is taken 0. Therefore, you got positive angle. Therefore, you got plus. Okay. But this is always correct. This sign does not change. Always RC means then you will get admittance admittance is always A plus JB, but impedance is A minus JB form. But current voltage, I told you already that I cannot predict. It all depends which phasor is taken as a reference and what is its angle also. Okay. Then, but I take magnitude here, IR square plus IC square. Okay. Then tan inverse IC magnitude by IR magnitude. S is equal to V into I conjugate. Okay, S is equal to V into I conjugate. You know that VI at an angle of, you get minus phi. Yes or no? Because you're taking conjugate, right? So therefore, what you get S is equal to VI cos phi minus J VI sin. Please write along with me. Don't wait. Okay. Please write. Please write along with me. VI sin phi. This is P. This is QC. P is equal to again VI cos phi. Okay. V square into G, but IR square by G. QC is equal to VI sin phi V square into BC or IC square, this is magnitude, okay, by BC. If I draw the phasor diagram, please note down all those things, okay? Because now we have done so many things on the phasor diagram, I think you can easily follow. Don't wait, just write down along with me, okay? So let me list out the phasors to be represented I, IR, IC, yes or no? This is IR, right? This is IC, right? Voltage is same for parallel. Voltage V is taken as reference. Also know that I is equal to what? IR plus IC. This is the phasor addition. At the tip of IR, I need to add IC. So this is IR, nothing but V into G. Current leads through the capacitor, yes or no? V into BC. This is the resultant phasor. I, nothing but root IR square plus IC square. Yes or no? Okay. This is angle phi because I and V phase difference always. Now the triangle will become, because G plus JBC, upward because first quadrant. Now this triangle is downward because it is capacitive P minus JQ. P, that is V square into G, nothing but P. V square into BC, nothing but QC. Yes, nothing but P square plus QC square. Angle phi. Okay. From every triangle you can write, IR is I into cos phi, horizontal component. Vertical component, IC is I sin phi. Like this for every, phasor diagram you can write. Always you write G is equal to Y cos theta or cos phi. BC is Y sin phi. Yes or no? Similarly here also, Everywhere you write this. We have already experienced this, but still I'm just writing it. Okay, just a repetition. Okay, QC is fine. Like this, we can write all the relations. If you find the triangle, then horizontal component, vertical component can be written. Okay, so like this, you can proceed. So I stop the session here. Next session, RLC parallel circuit, and then we'll see a lot of problems on this fundamental. Understand all of it? Okay? So I stop it here.